We are happy to have Dongmin Gang. He is one of the organizers. We are very happy to have him, and he's the first speaker of the day. He will tell us about non-unitary TQFTs and 3D and Ingo for rank-0 superconformal field theories. So whenever you're ready, please take away.
Can you hear me?
No.
Yeah, thank you. So first I'd like to thank other organizers for giving me the opportunity. I think this is the only contribution to the workshop. So, yeah, so this is my plan of my talk. So first part is basically review of a very beautiful story between the developer in the very old time. So already 30 and 40 years ago. So this is I think this paper's Listek and Tribe's paper is the first paper who introduced the non-unitary TQFT, although they didn't know that it is non-unitary. So I briefly reviewed that this I reviewed this paper, and this is my first part. And the second part is the research talk. I will review some my recent papers, recent work with Hyun and Sungjae and Sungjun in the audience. And this is my plan. Yeah, so I understand this workshop is in between the school and formal seminar. So this part is some school lecture, and this part is you can regard as a regular seminar. And yeah, so maybe I will spend more time to motivate why I'm interested in this work. So I will spend more time in this part. And some of you are more familiar with this story. So I will give more emphasis on this work. So let me start with some basic histories. So yeah, the story starts from of course, Wheaton, and there is a very famous paper by Wheaton in 1989 or 88 or 89 that he started SCFT Chun-Simon series. And yeah, so in this paper, he compute everything over Chun-Simon series, which is basically correlation function of the Wilson loop. And yeah, this is so one non-trivial example of the TQFT quantum field we can solve exactly. And then the mathematician and this pattern function give nice some knot and three manifold invariant. And so mathematicians are interested in this paper, and some Atia snapped give us some formal mathematical definition of the topological field theory. So topological field theory can be thought as some group theory. There are some structure, and they should specify some conscious condition. And so Atia gave us some Atia's axioms which define a three-dimensional TQFT. And then let's take and try. So using this Wheaton's making this Wheaton's approach to more mathematical rigorously, they found some three manifold and the link invariant called the WIT invariant. Which will be denoted by the RK. And it depends on some choice of M and some link, framed link with the colored framed link. And the RT invariant. And this is what. And then later RT developed that this some rigid algebraic structure called MTC, modular tensor cartesian structure. From modular tensor cartesian structure, they found that they can construct the 3D TQFTs. These are the basic history. Yeah, so I'm focusing on this papers. So feel free to interrupt me if you have any questions. So yeah, this is a very old story, and this is a very somehow very well known to some people in the audience. but the emphasis is that this is not, first zeroth order understanding the WRT invariant, but this is not the whole story. So the thing is that this WRT invariant, one thing they did is that they make returns process more massive and big registry and prove that this is actually the three manifold and the link invariant. On top of that, they also find the new topological field theories. And so the WRT invariants are labeled by additional parameter, which is called M. So M equal 1 cases, M is integers, and co-prime to this number. Yeah. And so M equal 1 cases correspond to the returns paper, which correspond to unitary TQFT. But general N cases, it can be either unitary or non-unitary TQFTs. So I will introduce this invariant. And so this is I think, the first example of a non-unitary TQFT in the literatures. And so this is formally given, and just this paper find some new mathematical structure which is satisfying the Artias axiom. And so unlike Chern-Simons theory, there's no quantum field theoretic understanding of this invariant. So that's the main message I want to present in this review. So recently, so what we did is that we found that this WRT invariant can be computed as partial function of some quantum field theory. Surprisingly, this non-unitary TQFT partial function comes from some highly supersymmetric field theories. So namely, this three-dimensional N equal possible comparability theories. So this second part is the main message. So is it clear? Yes. Any other questions so far? Yeah. So first part, so I will give I will explain how to compute this one. Yeah. So then I will compute so non-trivial test is that we can compute this one very explicitly for general M and the general link complement, and then compare that partial function using this compile field theory, and we will argue that they agree. We will actually compute it for several cases, so we can argue that they are equal. The first part, I will focus on the computation of this one. Yeah. Yeah. Okay. So yeah, let me be more precise. So M equal 1 and K, and it depends on M and L and framing. So this is L is a framed link, and I will use already L is can be written as these are link. So there's I will not this component link. So if you're considering link in this kind of hop link, these are two components, and each are the one and two. And this also, to define this invariant, we also need some framing I will introduce later, framing dependence, and also we can introduce the color for each component. This I call this alpha 1 and alpha 2. And this comes learned from the for given K, alpha learned from the K. So this one, and in one case, this can be written as a path integral over SCFT Chern-Simons series. And Yeah, so this is can be written in this form. So we will count with these variables. So this is a Wilson loop in a spin half of alpha, and we are computing correlation function of this one. So we can solve it. So mathematical solve. This can give a prescription how to solve it, and this let's take and try. Yeah, so keep using the Witten's description, they make it proceed more rigorously, and they prove that this is actually three-manifold and not invariant. And in the procedure, they also found the one parameter family of this one, two parameters. So, but unlike this M equal 1 case, in general M, this invariant is also nice topological invariant, and this also satisfies this RTR's axiom. So it defines some SCFTs, but can we compute it from the so this is my main motivation of my talk. Yeah, so M equal 1 cases, yeah, we very well know that this is a consignment pattern function, but for general M, generally it can be non-unitary. So can we with some pattern function? That's the motivation. And our answer is that this can be computed by some very exact class of three-dimensional Fokker field theories with some topology that I'm going to talk about. Yeah. Yeah, so one simple answer is that one indirect answer is that we can compute this define a non-unitary SCFT, this define non-unitary SCFT. So according to this computation, and this also can be regarded as this can be constructed by the MTC algebra modular tensor category structure, and this also MTC can be come from the two-dimensional rational algebra. So in a sense that we have an indirect realization of this topological invariant from the field theory, which comes from the two-dimensional rational conformal field theories. We know that there is also non-unitary rational conformal field theories. And this contains some topological structure given by so-called modular tensor category structure. And according to this construction, this will define a three-dimensional SCFT. In this way, we can indirectly construct this invariant from the 2D physics. But the thing I want to ask is there any way to realize this invariant from the 3D quantum field theories? That's the question. I think this is a very natural question, but no one has answers until the very recently. Yeah, so is it clear? So that's the whole story of my talk. So yeah, I will compute this one from the three-dimensional topology quantum field theories computation. Yeah, more concrete example, I will focus on simpler example. I will focus on that yeah, so this will define a SCFT because it satisfies the RTR's axiom. So I will call this SCFT as SU2K and M. M equal 1 is just the SU2K consignment theory. General M, this is it's called the Galois conjugate of SU2. Okay. So why this called Galois conjugate is that this is a parameter by this M. With this one, this can be regarded as we introduce this parameter Q. M. So this is exactly M. So this is so in other way, this topological invariant, this RT invariant parameter by the primitive root of K plus tooth root of the unity. So different M correspond to different unit, so they can be regarded as Galois conjugation in a common sense, in the user sense. So this is yes. So for example, that as you will see, so if you see C2 K equals 3 and M equals -3, if we just look at the modular data, modular tensor category structure, and this can be exactly the same as the modular tensor category of the Liang to the SCFT times -1 consignment series. Yes, this is some non-unitary rational conformability, sometimes called the Virasoro minimum model M2 So this is a rational CFT, and this has a modular tensor category structure, and this modular tensor category structure appeared in this Galois configuration. So the Gaussian function also is this 2k equals 3 and m equals -3 on general manifold and the general link and the claimed link can be computed as this can be computed. This is nothing but our definition of the k and the m l alpha. This can be computed as a function on the Liang, on something like this one, and times some pattern function of on the same way. This times. So we can compute this Liang FT, general three manifold and the general with the general link invariant by just computing this that's a function and so in my talk, I will compute this quantity more concretely. In general, we can compute the arbitrary m, and this is the main quantity we want to compute. So yes, in principle, we can compute the arbitrary three manifold and arbitrary link. We can compute it, and I will give a description how to compute it. Then in the second part, I will introduce the three-dimensional T minimum. I will call the T minimum theory. This is a three-dimensional rank-0 theory. And this can be described by some IR limit of some simple n equals to gauge theory. Coupled to single chiral over charge one. So this theory, you will discuss has only n equals 2 symmetry, which is gauge group U1 theory, coupled to single chiral, very simple theories. And this theory is known to has a supersymmetric enhancement in IR, and this flow to the three-dimensional rank-0 CFT, which I call the T minimum. Then our main, and we can also consider A twisting. So topologically, if there is a n equal supersymmetry, and then we can, then our claim is that also we can consider general L. Our claim is that this is same as Liang. This is our claim. Is that our claim is that for general M and for general link, this is satisfied. This part can be exactly computed by using this, thanks to the work of the Lichtenstein tribe. But this part can be also some example of the M and the link. We can compute this one using so-called localization, and then we can express compute and they match it. So this will be support that. So I will claim that this is nothing but the Liang. Yeah, this is a main flow of my talk. Yeah, we can only cover this one. Yeah, so if this Q is not this is not primitive one, then this can be regarded as the primitive root of a different K. Yeah, so yeah, then the case it's very natural to that. Yeah, this M is not the this is not the one, then the M can be regarded. So actually, the more precisely, this is parameter by this variable, Q parameter, any rootable unity, but we are considering this is a primitive rootable unity of this one, then this corresponds to this. No, only K and this, yeah, this appears. Yeah. Yeah, case by case, and different M correspond to different color conjugate, and yeah. So yeah, there are infinitely many new class of the national non-unitary TQFT they construct. There are more non-unitary TQFT than the unitary one, because that the M equal 1 case it is always as it sometimes 0 K, so it is unitary, but generally M is non-zero. Generically this is a non-unitary. Yeah. So yeah, so in this paper they did not realize that this is related to some non-unitary TQFT, something like that. Yeah, please. Yeah. So they are very simple objects. So if we compute the some M is 3 sphere, and this is Hopper-Ring, then we compute S metric, and then and also T metrics, and for given S and T metric, then the only kind of many choices, and then we can check that we can compute that this is MTC structure is very rigid, so the S and T metrics sometimes uniquely determine that this yeah. Yeah, so my claim is that this all non-unitary TQFT can be realized some rank-0 CFT of the spherical angle theory. So there is a corresponding rank-0 CFT, which is a rank-0 CFT is that I should define that this as a CFT with no Higgs and Coulomb branches. So the Coulomb and Higgs branches are point-like. Generally, if we have a supercharge, then generally has a rich variety of the modal spaces. In the higher dimension, we expect there's no such a rank-0 theory. But 3D cases, so we recently found that this theory exists. And you have to do the topology twisting. So for general n equal 2 CFT, n equal 4 CFT, you can do topology twisting. But the resulting TQFTs are not following the arterial action. It is extended TQFTs. But the rank-0 cases, we found that this always satisfy the Asher's axiom. So in the sense that the genuine TQFT, So this theory is that we are considering IFX point, and there are lots of infinity class of the UV different discussion. So it's difficult to identify which case. So if we change the K to another number, different number, then it does not flow to rank-0 CFT. Maybe there are some very nice field description. We can give the rank-0 CFT parameterized K, which gives all this class. But I will explain that. That's the main part of M is no. So this duality invariant is defined for any root of unity. So if you say that the K equal 6, and if you choose K equal M equal, suppose that 2, then this can be, and this is Q is something like this. So pi I 2 over this is 8, and then this can be regarded as a Q equal exponential 4 over 2 pi I 1. So in this case, this can be regarded as to transition level K series, just n equal 1. Yeah.
No example.
Yeah, K equals 3 correspond to this particular Liang TQT. Yeah. Yeah. N equal 2, and this is some non-neutral TQT, which is some modular matrix very similar to Liang, but some complex conjugation, something like that. Yeah.
Not depend on endpoint through Q.
Yeah, only through Q. Yeah. 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 So if yeah, then there's M. Yeah. So if M is defined the model K plus 2. Yeah. Yeah. And the primitive. Yeah. So this is yeah, this one. And yeah, so and if any root over unity can be written as in this way, M and this are the co-prime, then this will define this one. So this M is defined so as my notation SU2 M equals same as SU2 M dot K plus 2. Yeah, yeah. So for given K, there's only finite Galois orbit. Yeah. Yeah, that's all. Yeah. So, so yeah. So rest of my talk is that I will review the computation of this partition functions and the volatility invariant the computation, and then the last part I will compute this partition function. Yeah, then I will check that this is explicitly can be done. Yeah. Yeah, it's a very closely related. So at least I know that the M equal 1 case is, we know that the very famous C is 2D chiral central charge is the K plus I forgot 3K. Yeah. So general M, there should be some closed form, but I don't remember now. Yeah. Some, yeah. So from just a C, you can easily tell whether this is unitary or non-unitary. Yeah. Okay, yeah, that's my punchline, and yeah, that's all the message I want to give you today. So the rest of my talk is just you can consider it as a bonus, and okay, so yeah, is it clear? So yeah. So the goal is that I will give how to compute these partition functions. Yeah, so let me start the easiest one. So this is first we solve the U1 to the K series. Yeah, this is much easier because this test integral, yeah, this is the simplest, so abelian Chern-Simons series. This is this Gaussian integration, and you can easily perform this Gaussian integration, and we can do the test integral very easily. So this is I will start the U1 Chern-Simons level K series, and I will, and then in the parallelly, we can do the similar calculation for SU2 Chern-Simons K, and then also compute the SU2 A to the M. That's my plan. Yeah. This is very old story. Yeah. So some of you may feel very bored, but yeah, I think this is a very beautiful story. So I want to review this part. So when I always give a seminar on this talk, so I only allowed for 1 hour. So yeah, I should skip this part, and this is my opportunity to review this beautiful paper. So yeah. Yeah, let me start the simplest one. So U1 Chern-Simons level K series. This is very simple. So we want to compute this partition function. M and M with L labeled by alpha. Star alpha. And the alpha is the alpha learned from the 1. And the first simplest I assume the K equal even. Yeah, so I only consider bosonic TKFTs. So fermionic TKFT, there are subtleties, so I focus on the bosonic TKFT cases. So this one is nothing but I just want to compute these pattern functions. Yeah, so to other integer cases, it corresponds to spin TKFT. So some structure doesn't appear in the spin TKFT. There's some modification in the spin TKFT cases, so I don't want to do this one. So K core, K core other cases is known to be spin TKFT, depending on the fermionic TKFTs. So there are multiple subtleties, so I don't want to bother with this. Yeah, this is just nothing but the Gaussian integration. So we can easily perform this integration. And yeah, so it's very easy to solve. But let me just the simplest one is that we can compute this one. This is expected value, so we normalizing by this. This is just a three-sphere pattern function, and this is a three-sphere pattern function with Wilson. Yeah, so some computing overall normalization is subtle factor. So I first compute this one. This one can be easily computed. This is Gaussian integral. Recall that Gaussian integral, we know that if we are doing the Gaussian integration, this is exactly just nothing but the half of a second term evaluated x equal set point. Set point. Set point means x minus this one. How is that? How is that? Yeah. So in the same way, we can compute this pattern function. So what we do is that we solve this equation motion of A. So this is equation motion A, and then solve the equation and put this pattern function into this one, and with a half over one half, then we get the answer. So this is very simple, just the one exercise. And particularly when we suppose that three sphere, then this is much easier because that we regard the three sphere as some compactification R3. So not is some located locally, then this locally can be regarded as just R3. So R3, then the equation motion is just nothing but you can easily check that the equation motion is that in the vector notation, this equation motion is nothing but Ji is we have some link, we have some knot, and we are considering the flow. We are considering the current along this link, and this is a current with the coefficient alpha, and this is nothing but the B field. So this can be solved by just the Biot arbitrary law, and then put this into this one, then we will get the answer. And the answer is that very simple. Maybe I should be careful. Yeah, I'm not sure this is plus or minus, and so this is called the linking number, Gaussian linking numbers. Oh. Link numbers can be defined as the this is R1 and R1, S1 and R2, S2 parameterize the parameter the not over K1, the kappa 1 and kappa 2. It's a kappa 1. And this is a linking number. Yeah, I should explain that. So this is why we need to introduce the frame choice. So this expression is known to be integers. This is basically computing the linking number between this one. So an alternative definition of this linking number is that so we draw the link to NOT. And each intersecting point in the drawing, it is P, two point, and we assign some sign on this crossing, and I will call this as -1. And the summing over this one, and there are two intersecting point, and this will give us some +1 and -1, +1 and +1, or -1 and -1, then this will give a linking number 1, like that. So linking number can be defined in this way. So this is well defined. This expression is well defined. When the summation is very dangerous when the I equal J equal cases. So to regularize this one, so we need to introduce the notion of the framing of NOT. So this one does not make sense because this term becomes 0. Some cases, S1, S2 cases. So how to regularize this one? The simple way to is kappa. Kappa is so we are imposing this we are considering because there's a NOT and K, and we are considering, so the one way to is that we are considering this as the K tilde. K tilde is not just displaced along the subsequent direction, like this one. But the displacement, displaying way is not unique, and this can be determined by so-called framing. Framing is basically we are assigning some normal tangent vector, the unit tangent vector, which is on the NOT, and this will give a natural displacement. So it's a framing. So assigning some normal vector is K, then this can be framing. So when we draw the NOT diagram, we will always use the blackboard framing. I think I'm going too in detail, but yeah. So we draw the knot. We should framing always that this normal direction is parallel to the blackboard. And then if you draw a knot, then it uniquely determines the framing. And so when I will draw this diagram, I already assume that this is using the blackboard framing. Yeah. So then this knot and this knot is as a knot, they are the same, but as a framed knot, they are different. So they are different. And if you draw the framing, blackboard framing, it is like the Möbius strip, and this is just the analog. So they are different. So this is a framing choice. So here, so we will regard this as this way, and this k tilde is obtained by the display using the frame. So yeah. Yeah, that's of course. So yeah, in this case, and yeah, we will, yeah. So it's always better to use that framing, zero framing, yeah. Anyway, it depends on the framing, and the framing dependency will be also very important factor of this one. So this is a framing invariant. So this actually here we also need to specify the framing. So now we now using this expression, we can compute this expectation value of the every link with the color link on the 3-sphere now. And then we will need to introduce the extend this all the 3 manifold and all the knot, and also including these factors. Yeah. So point splitting regularization of this classically, there's no, we don't need to. It should be part of the definition of QFT. Regularization, it depends on pattern function, depends on regularization scheme. So I'm not sure whether. So it's a definition of the observer. Yeah, it's a observer, Wilson observer. So to define the Wilson loop, yeah, So if we're considering correlation function of the Wilson loop, it depends on the framing of this Wilson loop. It is so. Yeah, so without introducing this framing, there's no way to define that this Wilson observers. Yeah, mechanically. Yeah, definition of the Wilson loop, definition of the loop operator.
There's a singularity, like a self-correlation.
Yeah, self-correlation.
Do point splitting, but that's ambiguous.
Yeah.
You can have the Wilson loop split and twist around itself. So you have to define this framing as part of the observer.
Yeah.
So there's just not a unique Wilson loop. There's Wilson loops which are different by frame.
Yeah. They are almost same observer with a slight.
So different framings are related by a phase. So if you change this framing, it's like self-linking nothing. You actually define it on the left, this which put the then framing is just there. It must be. It doesn't work without framing.
Yeah. I haven't thought about it carefully, but actually our knot is actually in one case this is oriented one, has an orientation, and maybe we should show some light or something like that. Yeah, I don't know. Yeah, I haven't thought about it. Yeah. But there, I think it's there should be notion of the 1 framing and the -1 framing, and maybe one natural case that is oriented cases, we choose this as something like this one. And for non-oriented cases, there's no difference between the 2 framing pattern function level and the maybe we can regard that as that's a good point I haven't thought about. And so to generalize this computation to general three-manifold and general link, and we will use the technique developed by the Atias. And this is actually the definition of the TKFT, and we will use this as a technique to compute all the partition functions. So Atias' axiom is that we know physicists know what meaning of this one, but repetition is difficult to explain TKFT. They give it as an axiom of the TKFT. So we know that if given three-manifold, TKFT give a closed three-manifold, we will give some complex number, which is called the partition function. So it's obvious. So in physics, mathematical definition is TKFT is something like that. If you give a three-manifold, it gives a number. We call this partition function. And if you have some two-dimensional space, compact space, then we will assign a finite dimensional vector space, which is called hyperspace. This is also very natural. So we are doing the canonical quantization on Riemann surface times the circular times time. Then we can always TKFT. We can always Hilbert space associated with the two-dimensional space. And the one non-trivial thing is that this Hilbert space only depends on topology, and it is also finite dimensional. So this is one crucial difference of the TKFTs. Finite dimensional, yeah. So yeah, general TKFT we can assign this way, but the crucial thing is that it only depends on topology or some framing choices or something like that. Yeah, so that's the difference. And if we are considering some three-manifold with a torus boundary, with the boundary of is a Riemann surface, and we assign some vector in this Hilbert space. So this is also very natural from the fixed point of view. So in this, there should be boundary condition dependence, and the boundary condition can be inserted as a bra, and the partition function can be regarded as a cat state, something like that. So can assign this one. And then another thing is that we compute the and another thing I should explain that if there is a mapping class group of a Riemann surface or some space, and this will be act on some unitary operator, some operators, some linear operator on this Hilbert spaces. So this will give us induce some symplectic transform, some canonical transformation on the symplectic, classical symplectic manifold, symplectic so phase space, and it will give some operation on the Hilbert space. And then finally, if you have consider three-manifold, closed three-manifold, which is obtained by gluing the two three-manifold with common Riemann surface boundary, then with the twist by this mapping class group, then this partition function can be computed in this natural way. Yeah. So using this one, and yeah, for physicists, this is very natural operation, and using this one, we can generalize this computation to arbitrary three-manifold. Yeah. Yeah, this is a definition of one of the definition of this genuine TKFT. But the extended TKFT, yeah, we can also consider extended TKFT, and we can consider infinite dimensional, something like SL2C Chern-Simons theory, not compact to Chern-Simons theory. Then the phase space is infinite dimensional, and yeah. But in this aspect, the Atias definition, this is not the TKFT. So if we are considering the topology twist, the n equal 4 CFT, then this Hilbert space topology twist partition theory is also can be infinite dimensional if the theory is not the rank-0 theories.
Did not change the boundary geometry.
Yeah, change the boundary. So it acts as some symmetry of the phase space. So this symmetry, phase space becomes Hilbert space after quantization, and this symmetry becomes some operators in the Hilbert space. Yeah.
That's clear.
Yeah.
Next slide, I need
Yeah, so we have some three manifold with suppose that we have a torus boundary, and we have a torus boundary, and we are gluing this three manifold together, N1 and N2, and this has two torus boundary, and there's a way to glue this one using the mapping class group. Mapping class group is the diffeomorphism from some torus to torus. So give us some mapping class group element, we can. So this manifold is defined in a way. So we are gluing the three manifold with the torus boundary with some SL2G twist. Oh no, generally, so if there's a Riemann surface, if this is it's a common boundary, and we can, yeah. And this partition function can be regarded as a element of Hilbert series of this Hilbert space, and this is also can be regarded this one, and then this way, and we can construct. Yeah. Yeah.
Then it's the manifold with manifold N with the boundary symmetry.
Yeah.
Is the possible set of N is possible also. It is finite dimension also.
Yeah, in the sense that is the Hilbert space is finite, is that there is some topological boundary condition we can assign is finite dimension in the sense that number possible n. No, there are infinity many n. So yeah, so Hilbert space dimension is finite, but the element is of course infinity. Of course, infinity. Yeah. So yeah. So dimension, finite dimension does not mean the finite set, of course. Yeah.
Turning the manifold N to the one field.
This one? That one? Which one? This one? Yeah, so this is so we are doing so suppose that we are doing partition function on this manifold. Something like a Chern-Simons series. And we should specify some boundary condition. And this boundary and the partition function depend on some boundary condition. And this boundary condition, so this boundary condition is the KET and the draw state and the KAIST state. Yeah, so in this way, so yeah, it will be more clear if you see the more concrete examples.
It's generally
Yeah.
So, but topologically, what you get from
So mapping class group is defined as a diffeomorphism up to continuous deformation. So it is a finite discrete set, something like SL2G, something like that. So this is a crucial difference in the topological field theory and the usual quantum field theory. And the usual quantum field theory, we can assign these operators for each element of diffeomorphism. But the topological field theory, it does not hold details of diffeomorphism. It is only depend on the global structure of diffeomorphism. And this is called the mapping class group. So if you're considering the torus mapping class group, this is SL2G. So So this is secret. Yeah.
How can we know the case as labeled by three?
I mean, it will be clearer in the concrete example I will give that. Yeah, that's the only closed manifold, compact closed manifold in the 2D-dimensional. So we can consider. Yeah, we also need the orientation to define the Hilbert space. So so we need some Chern-Simons theory defined on the only. So let me do the step by step, and so U1K Chern-Simons series. So U1K Chern-Simons series. So first of all, we do is that so physical observers physical observers are Wilson loop. I will denote this one, and this is a defined exponential of I alpha and Ka. Wilson loop. Yes, this is confusing. This K is and this here has Z2 ZK one-form symmetry. And this is generated by this Wilson loop. But this is a topological defect. Everything is topological in topological field theory, and the Gauge invariant topological defect. And this will give generate ZK operation. So this Wilson loops is labeled by only mode K because that there is some monopole screening of this Wilson loop charge, and it's only defined mode K, and this form of ZK one-form symmetry algebra. ZK one-form symmetry, and this is a side remark because that our main theme of our workshop is generalized symmetry. So this is it's my talk is related to generalized symmetry, and of course we are considering non-unitary non-abelian gauge theory. There's also lots of invertible symmetry appears. Yeah, so this is a general, so natural background understanding the generalized symmetry. Yeah, so it's very mark, and so we can do this thing step by step, and we only focus on the torus, and then the Hilbert space is just given by its finite dimensional. And this is so this is dimension is K dimension. So this can be obtained by the quantizing this phase space. This space is a tensor. This space is the space of flat connections. Equation motion is flat connection, and cross with the gauge quotient. And this can be parameterized at this I say X and P, which is the A equal X is theta 1 and P is theta 2. This is constant. P, X, and P is a constant, and so X and P is a constant, then naturally become the flat connection. And these are the only gauge invariant up to gauge transform. These are the only the flat connection on two torus, and then the large gauge transformation says that the X one. So this is a phase space is again the two torus, and the symplectic form reduced by this consignment exchange is nothing but so if you quantize this finite the compact phase space, then we expect to get a finite dimensional, and the dimension is proportional to the volume of this phase space. Is semi-classically, and this will give this phase spaces. Sorry. Yeah, I will explain to you. Yeah. So first up, we are still in this one and this one. So this alpha phase space can be regarded as that the alpha phase space is can be regarded as position phase space of the K of alpha. So we consider this as the position, and this is a momentum x. This is why I call this x and p. And then the wave function is a position basis is labeled by x, but x should be periodic. X should be periodic. So X should be periodic, and the dual momentum is quantized. Dual momentum is periodic, so X should be quantized. So this is why I call this in this way. And this alpha should be integer, and the alpha is periodic. So it should be take values in the ZK values. So this is Hilbert space expanded by this finite dimensional Hilbert space. Yeah, this is a torus Hilbert space. So for given torus, we can assign a k-dimensional Hilbert space. And similarly, we can give a general genus Riemann space. We can assign we can do the similar procedure, and we can bigger Hilbert space for higher genus, and the dimension is k to the g, and we can Hilbert space. But the torus cases we can easily obtain. And then the one thing I want to do is that this one. So let's consider simplest example, which is most relevant example, is the D2 times S1. It's a solid torus. Solid torus has two torus boundary. This is called the zeta 1, and this I will call this is a zeta 2. Zeta 1, zeta 2 is the torus, Labelling torus over the boundary. And so this should be element of torus. Then the percentical representation, if we do this kind of the percentical, this pattern function, this is not pattern function. We are considering pattern function on base transformation. And the torus, we should impose the boundary condition. The boundary condition we are imposing that this A become the A. This is the one. So this is the boundary condition, and so we are fixing this holonomy along this one. The more precisely, we are picking that at the boundary. Alpha. And this alpha level this boundary condition. Then this will give us a number, and we can interpret this as this overlap of this pattern function. Yeah, so this is very naturally we can explain the why this overlap. And maybe you can consider different boundary condition choosing this cycle, and this cycle is just change of the basis. So anyway, I will stick to this one, this boundary condition. Then you can easily guess that this becomes just so the n equal to 2 times S1. So one way to see is that when the alpha equal non-zero, so we are imposing some non-trivial holonomic boundary condition. It means that there's no flat connection along this torus. So there's no set point to satisfy this boundary condition because this is a shrinkable cycle. So this to be flat connection extended to the whole solid torus. This has trivial holonomy along this contractile cycle. So only alpha equal 0 can give a non-trivial values. Alpha equal non-zero, then there's no set point, and this becomes 0. The alpha equal 1 cases, and this will become just 1, and this becomes the 0. So we can consider S1 as this 0. 1, 0. And our alpha can be regarded as a D2 times S1. And exciting this time x1 along this Wilson loop. This Wilson loop. I will call this 0,1 with alpha. Alpha. Yeah. So I think I have to explain them more. So quantizing this Hilbert space, we obtained this Hilbert space, and this x and p operator likewise x as operator like x as operator as a coefficient, and the p as a momentum. So we can check that on this basis, x act on the alpha and this is IP is the alpha plus 1. And more generally, if we consider this is 0 and alpha p, then this will become p alpha. And if we consider this Wilson loop with PQ alpha, this is defined as a one porous. There is a gamma PQ cycle, and the quiz field in the alpha. And this is nothing but the exponential of px plus qp. Yeah, so sorry for the bad notation. And this is PQ and this X and P is totally different. So in my notation, W01 alpha correspond to the exponential I alpha P. Exponential I alpha P. So it shifts 0 to D alpha. So this explains this one. So I think this answers his question. So 0 corresponds to D2 times S1, and this 1 corresponds to D2 times S1 with the insertion of a loop operators, wave function. Yeah, so this is nothing but we are considering the pattern function on the D2 times S1, and with the insertion of this Wilson loop along this direction, alpha. 3 manifold, we will come back to the point soon. So insertion of this research of Wilson loop can be regarded as some removing this tubular neighborhood of the 3 manifold and the boundary some boundary condition. So in this way, we can regard this as a certain 3 manifold with torus boundary. Two torus boundary. So I'm very slow. But I think it's okay because for SC2 cases, we are doing almost same procedure, so we can skip the what? So we are almost live, and then so so far on we finished this part done, and this part is done only for one example, but I think it's just enough. And then I will move on to this part. And also I will also consider this support and class group SL2G is related by the SNT matrices related by the here's S is matrices. And so every SL2G element can be generated by the multiple of the S and T and its number. So it's only need to assign this S and T. So S operation. Cross. So this X operation is act like X, so it should act like this one. I'm not sure. Something like that, and T should and X. Sorry. Like that, and the T is the. like that. So, and this also satisfies SL2G relation, and this should be unitary and something like that. And this uniquely almost determined this S matrices. And so we can write down the S matrix, and the answer is that for this case is, this is very simple. T matrix always diagonal matrices. Yeah, and you can check that this satisfies this relation, and this satisfies so SL2G relation, and etc. So this is the answer. So finally, now let's move to this one. So yeah, let's move on. We are now almost. So yeah, so then finally, so let's consider that some n1 equal, find this one. And this is just starting with the 0 and the 0. Then we can consider this one. This is nothing but 1. And this can be regarded as a partial function on S type. So because that we are sorting the story towards, and we are gluing the boundary with the identity matrix, then we will get some S2 times S1. We are gluing 2 story towards, and then we will get the times S times S1. So S2 times S1 partial function is the 1. This is what is expected, and this is the non-trivial thing is that S of element. And this become the S00. The 1. And this is nothing but the partial function on this. Yeah, so it is rather difficult to imagine, but we are gluing the 2 solid torus. Gluing in a way that we are gluing this cycle to this cycle, and we glue this cycle to this cycle. The resulting manifold is actually 3 sphere. So one way to see it is that we are considering some S3 as R3 compactification. So here is this is for R3, and this we are considering the knot along this one, and this will form some solid torus, and its complement is also again a solid torus. Can you imagine? So another solid torus is this one, and the infinity is identified, and this forms a solid torus, and the remaining parts form a solid torus. And you can see that in this gluing, these spherical cycles are glued by unspherical cycle. So in this way, you can visualize that this is the 3 sphere cases. So U1K cases, so now we finally find the normalization of 3 sphere partial function. So we find is that using this one, that U1 consignment shell partial function. Now this sphere. Now it becomes the So now we can fix the normalization. Yeah.
Like partition function without or it's not an observable. You can always normalize one.
No, in 3-sphere it is different. It has a meaning of the entanglement entropy. So it has very entanglement entropy. It can be, yeah, 3-sphere pattern, round 3-sphere pattern function in 3D has very natural meaning. So it round 3-sphere pattern function compute the degree freedom. So under the algebra learning, this round 3-sphere pattern function always decrease. Yeah, so it's very, yeah, there's no, yeah, overall normalization.
What is that in this?
Yeah, so
What?
topological theory has a global entanglement. Yeah, this is one character property of the non-trivial topological phase of 3D. So globally entangled state, ground state are globally entangled. So this measures the log root k measure the entanglement entropy, some universal behavior of entanglement entropy. Yeah, so it has a clear meaning. So at least the 3-sphere case, 3-dimensional cases, 3-sphere pattern function has a natural normalization, and every unitary KFT 3-sphere pattern function has absolute value smaller than the 1, and the only trivial character theory has a pattern function is 1. Yeah, so there's normalization, and under the RG, this 3-sphere pattern function always decrease. Yeah, so yeah, 3-dimensional, yeah.
What are there's nothing wrong.
So if you are starting from the UV CFT, and we can on the UV CFT use.
This
Yeah.
real kind of theory. I don't care about other theories.
Yeah, but if you consider UV CFT and the deformation, we can over get something you want Simon series, something like that, deformation, relevant deformation. And here we can also sphere 3-sphere pattern function, and we can also consider this 3-sphere pattern function. Then always this 3-sphere pattern function is small. This one is smaller than this one. So this will give a constraint that if this CFT has smaller than the free energy of this one, then this never can flow to this theory. Yeah. Yeah. So 3D, 4D it is related to A coefficient, A theorem. Yeah.
No. Like local conversion can always subtract it and make it straight.
Yeah, but yeah.
Because that there is no local conversion that can render it to 1.
Yeah. So I don't know exactly, but yeah. Yeah. So yeah.
Exponential times monodimensional constant times volume, right? So that kind of counter is like exponentiate the volume type of dependent, but that 1/k is really a constant. So local renormalization doesn't hold that over.
Yeah.
Because that is this. Yeah. It's really just a number, not the volume sums. So
Yeah.
so it's not completely generic.
Yeah. It is. Yeah. So yeah, 3-sphere pattern function has yeah. Obviously have a.
Yeah, but 3-sphere, I don't understand that point because 3-sphere function for a general general quantum field theory, it's not guaranteed to be given by these three numbers.
So if you're considering CFT, then there's some component transformation 3-sphere, and there's in 3D. I remember there's a very so 3-sphere finite part of a 3-sphere pattern function is can be well defined, and this actually is one of the most important quantity of the 3-dimensional CFT. Yeah, and also another characteristic is that there's entanglement entropy, some universal part of entanglement entropy can be regarded as a 3-sphere pattern function. This is how people prove the F theorem. Yeah, so this factor is also very important. So yeah, mathematicians usually define that the velocity embedded normalization with 3-sphere pattern function is just 1. But this is, I think, a physically very ill motivated conclusion. Yeah, now we are almost almost there. And so one thing I want to emphasize that and we can also generalize this computation with the insertion of this loop operators, alpha and beta. And we are gluing the S matrix, so we are considering this operation as D2 times S1. And we are inserting the loop operators of alpha 0,1, dagger, it should be dagger, left side, and some S operation, and imposing and inserting the beta and 2 times S1. And this compute S alpha beta, this compute S alpha beta. And this one is actually, if we glue the 3 manifold, it becomes 3 sphere. And this inserted loop form a hope link. So another way to characterize this S matrix is that it is partial function on the hope link. So you can check that in this example. So my S matrix, where is my S matrix is? Where is I erased the S matrices. Yeah, here is S matrices. And this S matrix is exactly the same as this S matrix, this matrix computation with hope link. You can check that. And the T matrices. And another, so yeah. In this frame, this is 0. Yeah. In program, self-linking is 0, and and this is another definition T S matrix. Another definition of T is that I have to explain that T matrix capture the change of the framing under the this self-linking number. So this is a way to characterize the under the self-linking number. So it has overall page vector, and this overall page vector can be regarded that this is a fractional spin called the topological spin over this H alpha. This one is I want to explain this one, and you can check that this expression also give this one. Yeah, this one. So under the framing changes over this Wilson loop, then this will get an additional page fact, and this additional page fact can be regarded as this H matrix is H diagonal element of H, and this can be called the topological spin, because that so if we draw the caplet and this is so so this is in a sense that the two anion how the page vector changes under this mutating over these two components. So this is a fractional statistics of the characterized fractional statistics of anion. So this is a H alpha. So let me explain the one simple way to compute the S and T matrix is using the this property. So from that we can compute the S000 alpha S alpha beta normalized by this one by computing over this hope link expectation value, hope link expectation value. Hope link expectation value does not contain this one. So this is easier to compute expectation value. And this is an unnormalized one. So this corresponds to normalized by 3 sphere, and this corresponds to this one. And also H alpha can be obtained by this one, and comparing this one exponential and this one, and comparing, and this comes to exponential. So from this data, we can extract some partial data of S matrix and T matrices. And then this can be converted into full S matrix by requiring that this S matrix should satisfy that is permutation matrices. So it will fix the S up to sign factor, including all the normalization. And the sign factor also can be fixed by requiring that at least in S alpha beta, there is one component of this alpha. There is one component alpha such that this becomes always 0. So in this way, we can also fix the overall normalization of S alpha beta. So in this computation, we can fix the whole S matrices. And using these matrices, one, we can fix the T matrices up to overall phase vector, this one, C. Then this C can be determined by the requiring that something like that. Then we can determine the C mode A. So in this way, if you know this expected value, then we can determine the modular S and T matrices. Because we are requiring that this T cubic is something, so it does not can is a mode A. Yeah, phi I. We can only determine. T, yeah, this is so T can be determined up to third root over unity using this relation, and this corresponds to C equal mode A. So in this way, we can compute the so this one. Yeah. So I'm almost here, and yeah. So yeah, it's okay. Yeah. Yeah, I will take a break, and I will just finish the one. Yeah, I think that yeah. So yeah. May I? Yeah. So yes. Yeah. So yeah, I will take a break. Yeah. We now for sure we can compute this path function very easily, and then I will generalize to the only 3 sphere. So now next thing I should do is generalize to arbitrary 3 manifolds and generalize to SU2 series. And so yeah, don't worry. So this is what I expected, and we are almost done. We are literally almost done. So we finished this one, and then another manifold, general manifold, we can construct very easily using this result, using the mathematical theorems. So the thing is that we should first identify it as this one, this path function. We can compute the path function this one, and we'll identify this as so this is a so-called link complement. So we are considering the link, something like that. On 3 sphere, something like that, I will draw it's not. Yeah. This is called the figure knot. No, I draw it. Yeah. Yeah. So yeah, I can draw it. Yeah, something like that. Then and we are considering this is defined as tubular neighborhood it's not. This is tubular neighborhood, and we make it thick, and we remove it. So if you're considering 3 spheres with the unknot, then this becomes the solid torus. Yeah. So this is exactly what this is telling us. If you remove this tubular neighborhood, this is unknot, and remove this unknot, then we will get a solid torus. And in this way, we can construct the complement. And then one thing is that we can identify this partition function as this not invariant. So it's very obvious because that let me write down this partition function is something like the dA and the exponential. Three sphere and the insertion of some defect. Something like this one. Then I want to emphasize this is equivalent to the partition function of with the boundary condition. So boundary condition is that we have each component of that, and we are removing this tubular neighborhood, and there is one cycle called the meridian cycle. This is linking this number, and we are fixing the hologram with these linking numbers along this one. Boundary condition is given by this one along this meridian. I call this is a meridian cycle along this meridian cycle. We fixed in this boundary condition. So this is the definition of this one. So we have a knot complement, and there is several torus boundaries, and we are evaluating this torus boundary with this boundary condition, and this boundary condition is exactly this one. And they are the same because you can easily see that you can do the equation motion, and this will be a delta function like a source, and this delta function like source can be regarded as this holonomy defect. So this is some stuff. So although we only compute this three-sphere link, but using this one, we can construct the pattern function of the all infinite number of this n. Then what we do next is that we are gluing back to the solid torus to form a closed three manifold with some twist of SL2G. So we consider this manifold. So these are the for each component knot we assign some coprime numbers, primitive coprime number, which are labeling some one cycle on the boundary. So this is obtained by the gluing the knot complement. All the components. So each component we remove this two-bar neighborhood, and we are gluing back the solid torus with a twist of SL2G. With a twist of SL2G. So we are gluing back in a way that P. So for each component knot, so we have this is a meridian, and we will call this longitudinal. So this boundary torus, one cycles are parametered by the linear combination of meridian and longitudinal. And we are considering some primitive combination, and we are gluing this with cylindrical cycle of this solid torus. Then if we include all this component, then we will get a three manifold, which is different from the original three sphere. If we choose properly this one. So in my convention, if you choose the PQ as 1,0, this is just the gluing factor in the same way. So we will get the three sphere again. But if we choose a different combination, then we will get a different three manifold. This pattern function can be computed using this RTI axiom that D2 times 0, 0, D2 times the S1 pattern function 0, 0, 0. And some SL2G element labeled by P1 and Q1, each component. And computing with this link. This link can be computed by this one. And we know the all SL2G element, and then this solid torus by component in this way. The pi PQ is that the SL2G matrix, which is a component of this one. So for given PQ, we can decompose into the S and T matrix, and we are computing this one, and we know this pattern function, and we know this pattern function, then we will obtain this pattern function. And the mathematician says that every closed manifold can be constructed this way. So we solve everything. Yeah. So it doesn't take much. So that's all. So if you want to know this one, then the generalize into arbitrary three manifold, and the arbitrary linker is trivial. That's the thing. Yeah, so we finished So we can, and this Leshiteki and Troy papers, prove that this is for SU2 case, this is a well-defined notion, and this, so one non-trivial thing is that there is some M3 manifold can be represented a different way. And this construction should give the same answer. This is non-trivial part, and this can be mathematically proven. So this is So basic message with this one is that if once we know that this not invariant to three spheres, then we can, and the SL2G matrices, then we can construct all the manifold, this one. So this can be done. So, and the S and T matrix also can be constructed by this linker invariant. So if we once identify all the linker invariant to three spheres, then in the same way we can do everything. So SU2 cases, so the only thing is that we should find some linker invariant, then that's all. So not Yeah, I will use SU2 cases. I will do the same procedure what I did for U1 cases. So left to the Hilbert space. I will just give the answer. Like that. So unlike abelian cases, there's additional Z2 quotient. Yes, this is comes from the bias quotient of Z2 with some subtle choices, and this is yeah, this is this one. And here, so we can also introduce the exponential ix, which is the Wilson loop. Yeah, Wilson loop, and this one. And we can also consider this Wilson loop along the PQ cycle and alpha, maybe because they trace spin tree of exponential. Okay. We can consider this. These are the basic physical observer, and this alpha level also should specify this one. So there is only finite many simple object. So dimension of Hilbert space. So this can be standardized alpha to the. Okay, so this is this one. Yeah, so and we can also consider SNT matrices and yeah, I will skip this part because that we can reconstruct SNT matrix using the link invariant. So I will just give a link invariant computation, then they can reproduce this SNT matrix later. Yeah, then the only non-trivial thing we should do for SU2K case is that we are constructing the link invariant. So we compute this, I will call this as n=1. So n=1 and n=1K is defined by the L and alpha. And this level is SU2 spin, the spin of the observers, and we only do that computer is to. Then everything can be done in this U1 cases as U1 cases. And I will give an answer. Answer is very short, so I can give an answer. Then yeah, I will. So for SU2 cases, I will just give an answer. So this for alpha = 1 cases, all the 1 cases, we are calling the 3-sphere Partian function, and with the expectation value, not the absolute normalization, and yeah, alpha and link, yeah, Wilson link. So we are link. So this is I will give the answer. This is what I for is that this is yeah.
In U1 case, just having the PQ, then ordering of how many times wrapping P and Q doesn't affect because it's abelian matrix. In the case with SU2, it seems to depend on how many times we pass the one and how many times
Yeah.
other cycles. But so does it really just depend on P and Q or more?
P and Q and the alpha representation, and we can also consider some the P and Q does not need to be the primitive. Yeah, then this can be regarded as winding several times. Yeah. So
Yeah, but doesn't it depend on the ordering of whether you first lap balance first cycle and the second lap balance second.
Yeah, of course, they depend on the U1 case also depend on U1 case also depend on the WPQ at 0,1 and the W 1,0 does not commute. And this will give the factor Q over something like W 1,0 and the W 1,0. And this can be regarded as not sure point of view, and this is regarded as this and this is something like that. Under the crossing, this has Q factors. Yeah, this is 1,0 and the time ordering. If you consider this is time direction and time ordering, and this operator relation is in one case is this set by this relation. Yeah, so this is this. So they're non-commute. Yeah. So that's a good question because the generalizing this relation, we can define a three-dimensional SU2 cases not invariant. So this is basic relation. And the basic relation is that this one is just given by that there's some convention difference between mathematician and the physicist. So there is some sign factors, and this is and times, and I will find that Kaplan bracket not invariant. Yeah, then the Kaplan bracket not invariant is that this Kaplan bracket not invariant is a polynomial include this one and this one, and this is defined by two simple rules. First one is called the sky relation. This relation. And this relation literally comes from this relation. And in the SU2 cases, we have one more term. And we rotate the grid, and we will get this term. This Kaplan bracket is defined by this relation, local rule. And then using this rule, if you have a crossing, then we can remove the crossing, and finally we'll get some bunch of unknot. And then another character is that there is a link knot, and there is additional link, totally unlinked unknot link. And this will give a Kaplan bracket is given by the so using this simple rule, we can arbitrarily we can compute this Kaplan bracket. This can be written as a Q series. Yeah, so I'm done. So and then this is alpha equal 1 cases. Then how can improve the alpha equal 2 cases? That's also very simple using this fusion rule. So we know that this Wilson loop alpha equal 1 is same as alpha equal 2 plus alpha equal 0. This is just the 1 expected, and this can be computed, and this is what meaning this is one is that we have a knot, and we are doing framing, and we are copying this knot along these framing directions. This is called cabling, two cabling, and this is can be regarded as a link over, and then we can put the Kaplan bracket. Then this will give the alpha equal 2, and the alpha equal 3 in this case. In this way, we can construct every alpha. In principle, we can compute it. So alpha equal 1, all the colors are fundamental. Then this Kaplan bracket relation gives the so-called Jones polynomial, and this colored one we give the colored Jones polynomial. So using this rule, although computation-wise it's complicated, you can compute the arbitrary alpha and arbitrary cases. So then we can compute this, and then you can do this simulation. Same. We can compute S matrix and T matrix, and then. So now, yeah, sorry, but I almost finished it, and I will give the answer for this one. Sorry, yes, and then we should identify this as Q as or Q equal root of unity. Yeah, so we should then specify this one. And then you can easily see that the generalized non-unity TKT is just a represented by this one by M. M equal 1 is the SCFT substantially, and the general M will give the Galois conjugate of the, yeah. So once we know that this link invariant, then for general M and this pattern function different, and this will define the theory for R called SC2 K and M. This is pattern function. So yeah, that's all. So I will compute some one simple example. This and this is alpha and beta. This is Hopf link, and this can be computed by this relation that this will give just yeah, sorry for yeah.
Why that n factor in the Q implies
Yeah, so I will explain that. So using this M, and then we can compute S matrices, and the S matrix for unitary S matrix, there's a S matrix satisfies certain criterion, and for general M, it doesn't satisfy S matrix. So it gave like a non-unitary RCFT characters. Yeah, S matrix. So S matrix comes from this Hopf link. So one and this one, and this is a very non-trivial computation in this case for general computation, but this underframing this has these factors. So this one and taking this M and also taking the Q, and we will obtain the procedure I mentioned. We can obtain the S alpha beta and the T alpha beta over SC2 K M matrices. For n equal 1 cases, this S matrix is the very well known. You can check that. Black size and T matrix is okay, yeah, so we can consider. So this is the S matrix for K equal 1 cases, and this corresponds to, so one simple thing is that this S matrix, first column of S matrix has always positive value, real value. And this is signal that this S matrix is unitarity. But if you construct for other example, oh yeah, so if you consider S matrix for and we obtained that this S matrix can be factorized as S matrix of yeah, S matrix of Yang times -2 and the T matrix. So ST over T over S over. So that S and T matrix for one K is given previous, and the S and T matrix is given by the Yang model is given by the first column has a negative sign. It is a signal that this has a non-unitary modulus matrix. This is closely related to that is the sum of component dimension at the boundary RCFT characters has negative component dimension. So this is implied that and RCFT matrix T is oh yeah. So this will define some thing. So yeah. So that and I will finish that my talks that so what I will yeah I'm almost done and let me give a final comment. So yeah. So thing is that so my claim is that this Liang SCFT pattern function. Now we can compute this Liang pattern function on arbitrary M with and the L link. We can compute it using this computation. And then what we are claiming is that I computed this distance pattern function of the minimum model, minimal theory A on the manifold with insertion of the yeah, these are the cases. But unfortunately, there's no way to compute this one topology twist pattern function on the supersymmetric side. But some cases you can compute some manifold such as M is given by some 3 sphere and as type as 1 or more generally some degree P bundle over zero Riemann surfaces. In these cases, we can compute this one using so-called localization technique. And also we can dress with some Wilson loop, which corresponds to simple object in the A-twist theory. Then we found they agree that this always agree with this one for this 3 manifold cases. So although we don't know how to compute this one, general 3 manifold and general link, but we believe that this always give the this answer and this will give a quantum field realization of this non-unitary-SCFT. First found mathematician in more than 30 years ago. Yeah, that's a conclusion of my talk. And we can generalize the more class of the rank-0 theory, and then we can only apply there exists non-unitary-SCFT, and we can further go beyond, and we can also using the field theory description, we can compute some characters with some by computing this pattern function on some D2 times S1 with some holomorphic boundary condition. Then we can found that this becomes the characters of Liang RCFT, something like that. So in this way, we can also extract this field description using the boundary RCFT data. So yes, that's all I'm going to talk, and sorry for running out of time.